I'm Milinda Jayamaha, and here we are here to present Lab 2 Part 3. So Part 3 of Lab 2 involves a 74HC161 synchronous counter which we are supposed to make to count from 1 to 6. So what we do is we have to make use of the PE enabled input in order to basically reset the H74HC161 once the counter reaches 6. So how we have done this, we have used a 74HC161 here and a 74HC00 here, because the 74HC00 works as a readout logic. So what happens is, when the Q1 and Q2 outputs of 74HC161 becomes 1, this pass through the AND gates, and then this will basically is connected to the PE output, and basically when the counter reaches 6, PE is enabled low, and when PE is enabled low, the 74HC161 resets from 6 back to 1. So basically this is D0, D1 and D2. So basically this represents the place values of the counter. So this will be 2 to the power 0, 2 to the power 1 and 2 to the power 2. So we're going to show you how it counts from 1 to 6 by pressing this run button. So once you press it, it starts counting. It goes on repetitively until you press it again. So you're pressing the stop button. So what happens is it freezes at the point which was counting it. And when you again press it, it resumes counting. And you can see it resets when every time it goes to 6, it goes back to 1. And basically that's the objective of Lab 3. That's it.
Hi, I'm Ronald and I'm from Group 6. Today I will be explaining to you Part 4 of Lab 2. So as you can see here, the Part 4 of Lab 2 demonstrates the die module and its outputs using a 3-bit input. So as predicted here, the table shows and approves all the possible outcomes that the die can provide for the possible inputs that is going to be provided through the clock and the other inputs. And the table here demonstrates 1 to 6 digits. So basically, as you can see here, a die consists only of 6 possible values. So 6 binary numbers have been used to demonstrate the 6 possible outcomes here, as we'll be using 3 pairs of LEDs and 1 singular pair. So initially, to demonstrate 1, we'll need just A. So the possible outcome A will demonstrate binary digit 1, and to demonstrate binary digit 2 we'll be needing D, and to demonstrate 3 we'll be needing A and D. For 4 we'll need C and D, 5 we'll need C and D and A, and 6 we'll need B, C and D. So this is the possible outcomes that we have simulated through this table. So to further simplify this table, we have used K-maps. So the K-maps here have properly simplified the circuit, and we have obtained the minimal SOP. So the simplified circuit as demonstrated here and simplified here below shows the circuit shows the possible values and outcomes that the die module can give, and the design that has to be implemented through the circuit to obtain the possible values. So we have used the don't cares here for the values such as 7 and 0, because they do not exist on the die module. So the don't cares simplifies and shows that the value 7 and 0 wouldn't exist in the die module, and the rest zeros show that these values do not exist and do not come out of the possible outcomes, and the ones show out the possible values and outcomes that can come out of the die. And the circuit below demonstrates the design that has to be implemented to obtain the value of the die. So now we'll be moving on to Part 5 to demonstrate the circuit.
Hi, I'm Milinda Jayamaha, and I'm here to present Lab 2 Part 5. So for Part 5, basically we are going to combine Part 3 and Part 4. So in Part 3, we basically we made use of a 74HC161 counter from 1 to 6, and in Part 4 we made use of a die module. So what we're going to do here is we're going to press the run and stop button. So what you're going to see is the die module starts counting according to the clock, and with the same pattern as you can see with the 1 to 6 bit counter, and observe. So you can see here that when the counter comes from 1 to 6, the die module moves in a similar fashion that we have already explained in part 4. So basically when it's 1, the center lights up and then so on. So the whole objective of this is to basically produce an electronic die. So what we need to do is, currently the frequency is 1 Hertz according to the clock. So to make this random, what we're going to do is increase the frequency. So we're going to increase it. So basically what's happening now is the die module is basically just going from 1 to 6 at a very high speed. So basically we don't know what's going to be the outcome. So it's basically going to be random. So we have to choose a random number from the die. We're just going to press the stop button quickly and we end up with the number 5. And then what happens is we press it again. We let go. We end up with 6. So basically pressing and stopping the run and stop button is basically simulating a throw of a dice where you get a random number as the output. That's all.